Good morning friends, I am Pratyusha Chaudhary, Assistant Professor of GRIT. Today I am going to discuss about the number-based systems. Number systems and Boolean algebra. Under this first unit I am going to discuss number systems. Firstly the number systems are classified into four categories: decimal numbers, binary numbers, octal numbers and hexadecimal number. In the first video we have already seen the classification. Okay, decimal numbers. For the decimal numbers, the radix or base r is equal to 10. That means radix and base. The radix refers to the number of digits that the number system consists of. So this is having 0 to r minus 1 digits. This radix will decide how many number of bits that it must have. Okay, so the decimal number system will have 0 to r minus 1, that is 0 to 10 minus 1 digits in this number system. So 0 to 9 digits will be there in decimal number system. 0 to 9 numbers belongs to decimal number system. And then coming to binary number system, the radix is equal to r. It does mean that it will have the numbers from 0 to 2 minus 1. That is, there are 2 bits, that is 0 and 1. So we call binary bits. Octal number system, where r is equal to 8. That means it will have numbers from 0 to 8 minus 1, that is 0 to 7 digits. So 0 to 7 are the numbers under octal number system. Next, coming to hexadecimal numbers, the radix is equal to 16. That means it will have 0 to 16 minus 1 digits. That means 0 to 15 digits will be there. That is 0 to 9 and A to F are the digits in hexadecimal numbers, where A is decoded as 10, B is decoded as 11, C is decoded as 12 and so on. F is decoded as 15. Why do we have these characters instead of the numbers? Let me give you an example. Say for example, I am inputting my digital system. Say for example, this is my digital system. This digital system is taking input as 1, 2, say for example 5, 13, 14 and so on. So this is the input that I am passing to my digital system. How the digital system process this? If it is considering this 2-digit number as it is, then no problem. Instead of this, if it is considering it as 1, 2, 5, 1, 3, 1, 4, then the problem arises, isn't it? So when you have a 2-digit number, it is difficult to process to the digital system. So instead of having the digital the 2-digit numbers, we are having the codes as 13 is decoded as D. So 13, the encoded value is D. For 14 it is E. So instead of 1, 2, 5, 13, 14, we are passing input as 1, 2, 5, D and E. Then the digital system can easily understand that D is equal to 13 and E is equal to 14. That means that we want to process a 2-digit number. Then the digital system will give appropriate output. That is the reason we have the alphabets in hexadecimal number system. Next one is representation of number systems. For decimal number system, the radix we know that it is 10, or in smaller capital D notation we will represent the radix. In binary we know that it is 2 or B. Octal number system 8 or O. Hexadecimal number system, the radix is 16 or H. Decimal number system, say for the decimal number system will have numbers from 0 to 9. So any number 7241 of base D or base 10 we represent. Binary numbers 10111.01, something like this, of base 2 or B. Then octal number system, you must be very careful while taking the octal number system, because it will have 0 to 7 numbers only. So any number 1025.72 of base 8. Hexadecimal number system, the radix is 16. So any number like this, A 345.DF of base 16. This is how we will represent. Or We'll give another example. I'm going to give another example for hexadecimal number system of base 354.3f. Fine. That is how we'll represent. Then we'll see some examples under decimal number system. The decimal number system is the most common number system that we have been using from our childhood. Say, let me have an example. Okay, we have already taken an example. 7,241. How do we represent this? 7,000 plus 200 plus 40 plus 1, isn't it? That means it is 7 into 10 power 3 plus 2 into 10 power 2 plus 4 into 10 power 1 plus 1 into 10 power 0. That means it is equal to 1. So always at units place you will be having least significant digit or least significant bit. And the leftmost bit is called as most significant digit or most significant digit. So in decimal number system, each digit in the number system will be expressed in terms of powers of 10. So this is 10 power 0. From LSD you have to note down this. 10 power 1 and 10 power 2, 10 power 3. This is how we will represent. Let's take a fractional number so that it will be very easy for you to understand. Example 2, 731.23. So you have integer part and fractional part. Integer part and fractional part. How do you represent this in decimal number system? 731.23. So the weights are going to be, this is 10 power 0th position, this is 10 power 1 position, this is 10 power 2, isn't it? 700 plus 30 plus 1 as decimal points, it is 10 power minus 1 and 10 power minus 2. So every digit in the decimal number system is expressed in the powers of 10. These are called as weights. Weights for each digit. So the weight for the first digit is 10 power 0. And this is 10 power 1, 10 power 2. This is 10 power minus 1, 10 power minus 1, 10 power minus 2, and so on. That is how we will represent the decimal number system. Coming to binary number system, let's take an example. 1011. Or no, we'll take some more bits. So let's take this as an example. This is having 1, 2, 3, 4, 5, 6. 6 bits in it. So we represent the radix also. This is in radix 2 now. We have already discussed that the radix represents, the number represents, each digit or each bit in the number system will have the powers of its own radix value. So this is having the radix value, the first bit is having weight as 2 power 0 and this is having 2 power 1. From LSB, least significant bit onwards, you have to start taking it. It is 2 power 1, 2 power 2 and this is 2 power 3. This is 2 power 4 and this is 2 power 5. That implies 1 into 2 power 5 plus 0 into 2 power 4 plus 1 into 2 power 3 then 1 into 2 power 2 plus 0 into 2 power 1 plus 1 into 2 power 0. So this is how we are going to compute the value which is in the binary number system. Is this clear? Let's take another example. 1011.101. Then the weights for this first bit is 2 power 0 and then this is equal to 2 power 1. This is 2 power 2. This is 2 power 3. This is 2 power minus 1. 2 power minus 2. And this is 2 power minus 3. Coming to the value, we will compute this way. So it is 1 into 2 power 3 plus 0 into 2 power 2 plus 1 into 2 power 1 plus 1 into 2 power 0 plus 1 into 2 power minus 1, which is half, plus 0 into 2 power minus 2, that is 0 divided by 4, plus 1 divided by 1 into 2 power minus 3, and then you can have its value later. That we'll see in the conversion sign. Next, octal number system. Let's take an example for an octal number system. 748.38. Is the correct? Is this the number belongs to octal number system? Tell me the answer. No, because the octal number system will have numbers in between 0 to 7 only. But I have a number which is more than the range. So it is not an octal number to be considered. So we'll take a simple number 0.23, which is an octal number system. Yes. Its weight is 8 power 0, 8 power 1, 8 power 2. This is 8 power minus 1, 8 power minus 2. How do we compute? 3 into 8 square. Yes. Plus 4 into 8 power 1. I hope you are getting this, right? Plus 2 into 8 power minus 1. 3 into 8 power minus 2. So that is how we are going to compute its value. That we will see in the time of conversions. And hexadecimal number system. Hexadecimal number. We know that the hexadecimal number system will have the numbers from 0 to 9 and then A to F. So let's take an example for hexadecimal number system. A, C, 2, 4.37, which is an hexadecimal number system. So the weight for, I told you already, we call it as weights. So the weight for the first digit is 16 power 0 and the next digit is 16 power 1. Next for C it is 16 power 2 and for A it is 16 power 3. For 3, that is after the decimal point, that is for the fractional value digits, it is 16 power minus 1 and 16 power minus 2. Now I hope you know how to calculate it. So A into 16, that is equal to A into 16 cube plus C into 16 square plus 2 into 16 power 1 plus 4 into 6 plus 4 into 16 power 0 plus 3 into 16 power minus 1 plus 7 into 16 power minus 2. Now you have to substitute its values. We know that A is decoded as 10. So you can now substitute the values. A is equal to 10 and C is equal to 12. Any more alphabets here? No. So that is how we are going to compute it. Yep. So in the next video we'll see the number based conversions. How do we convert the number, convert from one number system to another number system.